All right, let's jump right into this explainer. We're looking at some wild new research that's making sustainable architecture actually truly circular. Imagine a world where the buildings we live in are essentially grown from the earth, and then, when we don't need them anymore, they just seamlessly dissolve right back into the ground, leaving zero trace. I know, it sounds a bit like science fiction, but a really fascinating study out of Durham University is turning this exact concept into a structural reality. Today, we're diving into the cutting-edge science of enzymatic recycling in earthen construction. So, earthen construction. Human beings have been building homes using rammed earth and compressed blocks for literally centuries. And it seems perfectly green, right? Well, until you hit a pretty massive modern roadblock. You see, to stop these buildings from just washing away in the rain, builders today almost always add cement to stabilize them. But that creates a huge carbon footprint. We're talking comparable to low-grade concrete. And even worse, cement chemically binds the soil together in a way that makes it nearly impossible to separate back into its original components. It essentially ruins the soil's natural ability to be infinitely reused.
Okay, part one, reuse versus true recycling. To actually fix this cement problem, we really need to rethink our vocabulary. People use reuse and recycle interchangeably all the time. But in material science, they are entirely different beasts. Look, if you just crush up an old cement-laden block into coarse rubble and use it as a filler, that's just reuse. You're basically downcycling the material. True recycling, on the other hand, means we're covering the exact original, pure soil fractions, getting back the pristine sand, silt, and clay in their exact original quantities, so you can build a brand new block of the exact same high quality. Cement makes true recycling impossible. But what if we replaced cement with something the earth naturally knows how to break down?
Moving on to part two, biopolymers as sustainable stabilizers. To ditch the carbon footprint of cement and actually achieve true recycling, builders are turning to nature's own chemistry. Now, in this rigorous Durham University study, the researchers didn't just go out and dig up random earth. They used a highly specific, standardized engineering base called Soil 271. It's carefully calibrated, 70% sand, 20% clay, and 10% gravel. By using this exact baseline, they could accurately measure if they actually succeeded in recovering the original soil after mathematically breaking down the blocks.
So instead of cement, they mixed the soil with biopolymers, specifically guar gum and xanthan gum. Guar gum actually comes from a bean plant, and xanthan gum is derived from bacteria. Honestly, you probably eat them every day. They're in most salad dressings and ice creams. But in soil, they are highly hydrophilic, meaning they absorb water and form these incredibly powerful hydrogels. They essentially act as a sophisticated biological glue. They interlink the soil particles perfectly, giving you compressive and tensile strength comparable to cement, but totally without that devastating environmental impact.
Which brings us to part three, the enzyme recycling breakthrough. Here's the catch, though. These hydrogels, they are incredibly strong. If we want to recycle the building and we just try washing these blocks with water, the clay and silt stay stubbornly glued together. Enter the major breakthrough of this study, an enzyme called β-mannanase. If guar and xanthan gums are our biological glue, β-mannanase acts as highly specific biological scissors. Both of those gums contain mannose monosaccharides, and this enzyme is perfectly designed by nature to target and snip those exact chemical bonds. It completely unlocks the hydrogel without damaging the underlying soil at all. To put this to the test, the researchers set up a really meticulous two-stage washing process to separate the soil from the crushed blocks. Stage one was just a standard soak and wash using distilled water pushed through a very fine 63 micrometer sieve. And just as they expected, water alone totally failed to release those fine clay particles. But stage two was the main event, a targeted 24-hour soak and wash using a 1% solution of the β-mannanase enzyme. When you look at how this methodology maps out, you can clearly trace the progression. From breaking down the physical samples with a rubber hammer, moving through that initial stage one water wash, and then, crucially, dropping right into the stage two enzyme wash. It perfectly highlights that the enzyme is the essential chemical key to unlocking the finer soil fractions that water alone simply couldn't budge. Part 4. Recovering the original soil. Let's look at the actual physical proof in the soil itself, because the results were amazing. The biological scissors worked exceptionally well, especially on the guar gum stabilized soil. By snipping those hydrogel bonds, the enzyme completely freed the original sand, silt, and clay.
And even more impressively, when the researchers measured the soil's Atterberg limits, which is essentially its plasticity or how the soil feels and acts when mixed with water, they found that the enzyme wash returned the soil's physical behavior remarkably close to its pristine, unamended baseline.
Looking at the particle size distribution here, you can see the physical sizes of the recovered soil grains. Check out the blue and red lines compared to the green baseline. That green line is our original 2:7:1 soil mix. Now, after the first water wash, the curve is way off, right? That's because the clay is still glued together in large chunks. But after the enzyme wash, look how that curve shifts dramatically back to the left, hugging the original green line. It is undeniable visual proof that the exact distribution of soil particles was recovered. True recycling literally achieved. And they didn't stop there. The researchers successfully took these exact recovered soil fractions, mixed them with fresh biopolymers, and rebuilt these structural earthen test cylinders. Think about that. They chemically melted them down, extracted the pure soil, and built them right back up again. Now, there was a slight drop in compressive strength for the Guar gum after multiple cycles, but the blocks maintained excellent structural integrity, staying well within the safety guidelines for earthen construction. Finally, Part 5, the regenerative building future. This actually brings us to a fascinating secondary discovery. What happens when we push this process and loop it over and over again? Well, the researchers noticed something pretty wild about xanthan gum. Because it forms stronger ionic bonds, it was a bit harder to fully separate with the enzyme than the guar gum. But in return, it revealed a complete superpower. Xanthan gum is regenerative. Even after multiple loops of chemical destruction and physical rebuilding, the residual hydrogels actually coherently bonded with the newly added biopolymers. It maintained and in some tests even increased its tensile strength through multiple cycles. So ultimately, this study proves that using biological scissors to cut biological glue isn't just some academic theory. It's a highly practical, scientifically validated blueprint for true recycling in the construction industry. By leveraging β-mannanase, we can quite literally strip away the structural glue of today to harvest the building materials of tomorrow. I'll leave you with this final thought to ponder. If we can standardize the use of engineered soil mixes, stabilize them with food-grade biopolymers, and unlock them at the end of their life cycle using targeted enzymes, we aren't just building structures anymore. We are farming our architecture. We are creating a truly circular, zero-waste life cycle where a building can be infinitely melted down and regenerated. It completely redefines what it means to build sustainably. Thanks for joining me to explore this incredible material science breakthrough.